All right, let's talk about one of the most fundamental forces in the entire universe. It's totally invisible, but it can make tiny particles perform this beautiful, intricate dance. So how does magnetism actually work? Let's get into it.
So let's just start with a question to get you thinking. Picture a single charged particle, just flying through totally empty space. What kind of invisible force could possibly reach out, grab it, and swing it around in a perfect circle? I mean, with absolutely nothing physical there to guide it. Well, the answer, of course, is magnetism. And how it pulls this off is, frankly, an amazing bit of physics.
To really understand this dance, we first have to understand the dance floor itself. And in the world of magnetism, that dance floor is this invisible, all-encompassing field of influence.
So what is a magnetic field? Well, it's just the space around a magnet or, and this is super important, a moving electric charge where you can feel its magnetic pull. It's kind of like feeling the heat from a bonfire without actually touching the flames. It's this invisible force that just radiates out from the source.
Okay, so that brings us to a really key point. Where do these fields even come from? Well, it turns out there are basically two fundamental sources that create all the magnetism we see anywhere in the universe.
So on the left, you've got the one we all know, right? The permanent magnet, your classic bar magnet with a north and a south pole. But on the right, that's the one that's even more fundamental. It's just a single moving electric charge. And yeah, you heard that right. Anytime a charged particle moves, it actually creates its own tiny little magnetic field that kind of swirls around its path. Wild.
Okay, so we have a field. Now, how does that field actually push or pull on another charged particle that's just passing through? This is where things get really, really interesting because the rules, they are not what you would expect at all.
And here it is. This is probably the single most important and, frankly, the weirdest rule of magnetism. The magnetic force doesn't push a particle forward and it doesn't pull it backward. Instead, the force is always perpendicular. It's always at a perfect 90-degree angle to both the direction the particle is moving and the direction of the field. It always pushes sideways.
So here's the deal. This whole sideways push thing only works under a few conditions. First, and this is the big one, the charge has to be moving. If it's just sitting there, a magnetic field does absolutely nothing to it. Zero. Second, that sideways force is at its strongest when the particle's path cuts right across the field lines at a perpendicular angle. And third, if the particle happens to be moving parallel to the field lines, again, nothing happens. It feels no force at all. It just sails right on through.
Now, physicists have this nifty little trick to figure out which sideways direction the force is pointing. It's called the right-hand rule. But you don't really need to get into the weeds with that. The key takeaway is simple. For a positive charge, the force goes one way. And for a negative charge, like an electron, it gets shoved in the exact opposite direction.
Okay, so let's put it all together now. We've got these strange rules, this constant sideways force, the fact that the particle has to be moving. What happens when you combine all of that? Well, you get something really beautiful and surprisingly predictable, the magnetic dance.
All right, before we see the dance, you need to know how to read the diagram. It's easy. In physics, when you see a field of dots, just imagine arrows pointing straight out of the screen right at you. And when you see a field of crosses, that's the tail feathers of the arrows, so the field is pointing into the screen, away from you. Got it? Cool.
And here it is. This is the magic trick in action. Look at that positive charge coming in from the left. Its velocity is to the right, and the field is pointing in. So that perpendicular rule we talked about means the force pushes it up. But wait, as soon as it starts moving up, its velocity changes direction. And so the force also changes direction to stay perpendicular. Now it's pushing it left. This just happens over and over and over again, a constant sideways push that never speeds the particle up, never slows it down. It just keeps changing its direction, forcing it into a perfect circle.
The source material really just says it perfectly. It doesn't matter where that particle is on its circular path, that magnetic force is always acting like a tether, constantly pulling it right back toward the center of the circle. And this type of center-seeking force has a name in physics. It's called centripetal force. It's the exact same kind of force that keeps a satellite in orbit around the Earth or keeps water in a bucket when you swing it over your head. So in our case, the magnetic force isn't doing anything mysterious. It's just providing the centripetal force that's needed to keep that perfect circular motion going. So we've seen how one tiny particle does this dance. But what's so cool is that this principle doesn't just stay at the microscopic level. Oh no, it scales up to shape our technology and even our entire planet. When you boil it all down, this is the fundamental feedback loop of magnetism.
Moving charges create the fields, and then those very same fields turn around and steer other moving charges. It's this elegant cycle that's responsible for so much of the world around us.
Look, this particle dance is not just some textbook theory. It's the very principle that used to paint pictures on old tube televisions, and it's how we smash atoms together in giant particle accelerators. On a cosmic scale, it's what generates the Earth's magnetic field, the very thing that protects us all from the solar wind. So the next time you see a simple compass needle swing north, just remember the invisible dance that's happening all around you all the time. Makes you wonder, where else do you see it at play? Thanks for tuning in.